maybe you don't get into the depth of the topic all that much. All right, let me turn off my music. I had this all beautifully integrated, and it's just not working, so I have to do this old-fashioned way here and just turn the puppy off. All right. So what's your relationship status? Okay. Please turn off all your sounds. No. If you want to share your relationship status with the class, that's up to you. I can put you on the mic, and then, we can. Alrighty. So my name's Shelly Kauffman, and I teach, at this point, mostly non-majors classes at Albright College. So I'm really used to a crowd that comes in, usually to my class. Half of them tell me they hate science right off the bat. Usually at least 2 tell me they hate nature. So I like to take them into the field, and I like to take them out. I'm a geologist by training, an environmental scientist through my graduate school training. So I like to be outside, and I like to take students outside. So being in this environment for a week is probably going to make me a little batty. So by the end of the week, I'll be the one pulling my hair out. This is I did not choose the standard that we're doing. It was handed to me, but this is the standard that we're going to be working on when you're with me. We're looking at processes, how the Earth cycles things. So we're basically going to do this in 2 segments. We're going to do a piece today that is focused on the meteorology component, and we're going to do a piece later in the week that is focused more on mantle convection and geologic processes. All right, so everyone has, hold on, let's pull this up first. Notice that we had a little bit of change in the weather over the last, usually this time in Pennsylvania, we can expect lovely, hot, humid, hazy, and it's gorgeous outside today. So why is it gorgeous outside today? Well, hopefully by the end of this hour and a half, you'll be able to answer that question pretty easily if you already can't, because who's a weather junkie? Who watches the Weather Channel? Like, my husband is a weather junkie. He drives me insane, but I can kind of appreciate, after reteaching myself some meteorology this week, where he was coming from. So this is a nice animated NOAA map of all the various fronts that had come through, and this actually projects, I think, a little bit into the future. Let's see, Monday. But you can basically see what happened. Who's from Philadelphia? All right, what happened in Philadelphia yesterday? In your weather. Yeah. Do you know they actually experienced the highest amount of rainfall in Philadelphia in a 24-hour period ever recorded? Philadelphia, as you know, has a very deep history of science. They have probably one of the longest recorded rainfall records in the country. They recorded the highest ever, over 8 inches of rainfall yesterday in Philly. We had this amazing front come through. This is kind of what we're going to work toward today. So I'm going to do something that teachers never ask you to do, and that is I would like you to pull out your cell phone if you have one. If you don't have your cell phone, you can pull out your iPad. And we're going to do a little bit of online polling just to kind of see, so I know where you're at. Some of these questions will be so painfully simple, you'll say, is she kidding? Other ones may or may not. So let's see if this works. Oh, first, I forgot. First, we're going to look at, this is so painfully true. This just came through on my Facebook page like a week or 2 ago. This is so true. My kids, I have an 11-year-old and I have a 14-year-old. And it doesn't matter what we're doing, and my husband's a scientist too. So it doesn't matter what we're doing. Every dinner conversation turns to something with science. And we sit at the beach, we sit at the lake. Why are the waves so big? Why can't we go out in the kayak? Well, let's talk about fetch. So I don't know. I'm sure you guys can appreciate this. You just don't look at the things through the same lens when you're looking at them as a scientist. So it makes beach vacations a little less relaxing. All right, so here is the first thing we're going to do. Have you guys used Poll Everywhere before? So basically what you do is, here's the question. Hot air is more dense or less dense than cold air? If your answer is that it's more dense, this is the number you're going to text to. So this is the contact, 37607. That will remain the same. You're going to text this value if you think this is the content of your text. This value if you think it's less. And if you don't want to use your cell phone, you don't want to use your data, you can do this at pollev.com as well. And what should happen if this works correctly is as you guys are responding, I'll see an immediate feedback from what you already know. So this enables me to kind of gauge where we are before we start. Maybe that'll help keep the cold air in. And so far we've got, all right, a few responses. You text, okay, if this is what your answer is, okay, so this is the phone number you're texting to. So this is your contact. Text this code to this number. Yeah, I did a great job of instructing that. If you're online, go to pollev.com, and it should give you, I haven't actually done that. Did you type, is that what popped up when you did pollev? You know what, I haven't actually used the site. Don't worry about it. Here, let's try this. Maybe that'll. I was hoping it would just give you a screen where you could type in. Yeah, here you go. Yep, there you go. Okay. So far we're in pretty heavy shape of less. So, again, don't look at the answers before you answer. No. Don't look at the answers. Don't wait for answers to pop up here before you answer, okay? I want honest answers. Obviously, this one, if anybody gets this wrong, then we're in trouble. Let's go to the next one. Let's see what we only have 14 responses. So some people didn't respond or are still processing. There's 16. It's a little slow. Or what happened? Wait, you're on an iPad too, right? Let me see.
This is what mine shows for pollev.
Now yours is working fine and yours is not. All right, don't sweat it. Just here. Let's do this.
Code or keyword.
Can you delete that? And that didn't probably help. Yeah, don't worry about it. I don't know why that is bizarre. Is that an old version of an iPad or something? Does it have? That could be it. I know. You don't even have a camera on the iPad one, do you?
No.
Oh, don't you love Apple? All right, let's move along. I don't want to spend all morning on this, but let's go to this one. If it's not working, don't sweat it. Just don't enter. But the next question is: humid air is more dense or less dense than dry air? If your answer is more, this is the code you're going to text. If it's less, this is the code you're going to text. Uh-oh, that's okay. I can't know who answered. I can't grade you on this. It's really just for fun. Don't sweat it. Ironically, you probably gave me the right answer by accident, so I need to erase. Just need to remember to get rid of these before the next class. Alrighty, so we think that humid air is more dense. All right, we'll investigate that. One of us thinks it's less, and one of you told me you did the wrong answer, so I won't ask you which way you went wrong. All right, now this one, these maps are a little tiny. Just trying to squash this all on the slide. But you're asked which of these maps best shows the pattern of surface winds around these two pressure centers, high pressure center, low pressure center. So look at the arrows carefully. Tell me which one of these is correct. This is the North Hemisphere. That is US. This one requires a little bit more thought. So the arrows up here are going like this. The arrows here are going like this. If you don't know, you don't need to send, or just send something in. Send your best guess. Well, good. I'm glad we don't know everything before we get started, because then it would be just, you know. If you're having to think about it, that means I'm hitting this target with what we're going to talk about today. See, I don't know, you guys probably, yeah, you don't have, most of your kids don't have cell phones accessible when you're teaching, right? Or do some high schools allow the kids to have them with them or not? Most just say, put it in your bag, I don't want to see it. So if you said to well, not every kid has a cell phone too. I mean, there's also that. There's also, actually, most of them usually have better phones.
But I was specifically told this past year I was not allowed to use it.
Okay. See, those are the joys of being a college professor. You know, your rules are a little, that's exactly it, less restrictive. So this may not be a great practical application for you guys to use in your classrooms. However, there are other places you can imagine this would be useful. If you're doing a tutor session or something, or you're teaching an outreach program, or you're trying to teach adult classes, later in your career when you go on to actually do some teaching outside of your school environment. All right, so far so good. So the next one, we're looking at this question, but I put this back up here for reference. So the question is, in the next few days, the arrows on which map show the most likely path which these two pressure centers will move over the next few days? The cool thing about this is I could actually send a command to Poll Everywhere from my cell phone, tell it to send me the results, and then I have all the results saved. So if I wanted to know what, if I can't remember, oh, this class really missed this, or this group really didn't know this when we started, then I could get these results from them. And Poll Everywhere is free. Up to like 40 responses, so if you have a class bigger than 40, which I hope you don't ever, but it's 40, I think. 40. They might have upped it since. All right. We're still getting a few. I love how it readjusts the graph over here, too, for every time you put something in. If life was so flexible, it would be nice. All right, so most of us think that this is the scenario that's true. All righty, very good. Now, this one is actually a topographic map. So my question for you is, at which point, 1, 2, 3, 4, 5, they're in purple. So there's 1, 2, 3, 4, and 5. Which point on this topographic map, these lines represent the elevation contours. Where's the steepest point?
So you finally got a room, and I'm going to interrupt you in the middle of your presentation.
Okay.
I'm sorry. You're not getting out early for lunch, but 12:25, we're staggering that.
12:25. Okay, guys, remind me when we get there, because I won't.
And also, tonight's performance for the Irish dancers, I have tickets. If you don't mind, if anybody wants one now, you can grab them. If you're local.
All right, looks like you guys are pretty good at, here, just go ahead and pass them out. And
Okay.
I'll keep going.
Keep on.
Yeah.
Just raise your hand. Tell me how many. Come on.
Looks like most of us know how to read a topographic map. But we're going to touch on this too in just a bit here. All right, sure. Oh, one more. I thought we were done. I forgot. Oh,
I didn't put it in yet.
that's okay. It's fine. We're getting the gist of this. It doesn't need to take up. All right, so the red letters is what we're looking for next. Which red letter would you expect the fastest velocity wins? These yellow lines represent lines of equal pressure. Don't worry if this all looks a little odd to you, because this is what we're going to talk, this is where we're going today. So I'm happy to see a little bit of uncertainty here. It means I do have something to teach you. We're all over the place with this one. Come on, somebody give me a D or an A just for fun. I know it's a bit of an arduous process to do all the texting thing, but I kind of like having this. I have not used this with my own classes because I just was at a technology course that was teaching us about this, so I'm kind of interested to see if I can incorporate this into my own classes this semester. Okay, we're going to move on from here. So, kind of two topics or two main themes that are going to be overarching what I'm talking to you about over our two sessions are the concept of density and the concept of, brain fart, gradients. There we go, that was the second one. Obviously, you know, you guys have run all sorts of demonstrations in your classrooms that play off this theme of warming air makes it less dense, enables it to rise because the pressure where this is taking place is pretty constant. Has anybody ever done this? I don't want to play this whole thing because we're going to be short on time today, but you guys will have access to these PowerPoints so you can see this, but there's a really nice example of looking at the density of Pepsi and Diet Pepsi. And this guy goes through in his high school lab, he puts the Pepsi and the Diet Pepsi in a big water tank. What happens to them? What happens? Which one sinks and which one floats? Yeah, it's lighter, right? Okay, guys. I know. I have corny jokes, so just be prepared. The Diet Pepsi actually does float because its density is less. But the neat thing about this video, it's not just a demonstration. He goes through the math. So he calculates the volume of the can. He calculates the mass. He calculates all these different things to show you very straightforwardly how density is calculated. Density is, of course, mass divided by volume. So I encourage you, if you want to kind of tie in a demonstration with the actual mathematical component of it, that's a nice little video. And he steps through the whole process. He has very nice handwriting, and you see all his calculations. All right, well, usually Pennsylvania's summers are very humid and gross, and of course today is the antithesis of that. However, when you walk outside into this hot, humid air, you tend to go, ugh, and you feel like you're hitting a wall of something thick, right? Which is why most of you suggested that the density of humid air is greater than the density of dry air. Now, why is the density of humid air in your minds greater than the density of dry air? Give me, it feels heavy. What else? There's moisture. So it feels like there's more in there, right? Who's a chemistry teacher? Okay, chemistry teacher, are they right?
No.
Why aren't they right? I'm sorry, I put you right on the spot. See, I'm hoping to learn like some good ideas from you guys because you are in the trenches.
Water vapor is less mass than nitrogen. Air is mostly nitrogen.
Bingo, beep, beep, ding, ding, ding in the back. Okay, so we have to remember that for a fixed volume of gas at the same temperature and pressure, Avogadro found that we would always have the same number of molecules no matter what gas is in the container. So we're going to look at two containers, one that has 10 molecules. Nitrogen in blue, oxygen in red. Chemically, we know that these gases are always found bound together. They're part of our, the gas, what do you call them?
Diatomic.
Thank you, diatomic. I don't know why, yes, thank you. I'm a geologist. I kept coming up with diatomaceous, and that's not the right word. Anyway, over here we replaced one of these nitrogens with a Mickey Mouse. What's our Mickey Mouse molecule? Water. It's water. What has more mass? 2 nitrogens or 1 hydrogen? Water. Yeah, let's look at it. So we know if we have 2 oxygens, they're basically 16 plus 16, that's 32. 2 nitrogens are, 18 altogether. I'm sorry, 28 altogether. Nitrogen is 14.
Right.
Okay, and then
Water.
Water.
Wa-
Water's 18.
water is 18, thank you. All right, so we take 32 plus 28, we replace this 28 with an 18 over here, right? So we've actually decreased the mass in this container by 10 atomic units. So what have we done to the density by putting water vapor into our container? We've decreased the density. So humid air, given everything else is constant, pressure, blah, 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 actually is less dense than dry air. And this runs totally counterintuitive to our experiences in life, right? It's kind of like, we use this sense of feel all the time. And sometimes that can send us in the wrong scientific pathway. A good example, I'll take a person. I need a person. Trying to find something metal. I need a person, a volunteer person. Where's a good piece of, here we go. All right, come up here, you're right up front. Okay, so close your eyes, put one hand on the desktop, and put one hand on this metal base of this desk. All right, tell me about their temperatures.
This one's a lot warmer than the metal.
It's warmer? Okay. Now, take the infrared gun, and don't shoot it at anybody because it's got a little laser beam, but this is basically like what food handlers use or food inspectors. It just basically takes the temperature of the surface. You can get this kind of thing for like $25 on Amazon. I don't think this one was a $25 one, but
15 at Harbor Freight.
okay, thanks. So go ahead and take the temperature there of the tabletop.
75.4.
Okay, what about the metal?
75.4.
So what did she just discover? The temperatures are the same. Her perception of that temperature was going through her hands. So why did the metal feel so much colder?
Because it's more inductive.
Thank you. Exactly. It conducts heat energy away from your hand. And so that makes it feel colder. The air feels thicker. That doesn't mean it's more dense. So you got to be careful with some of these sort of very intuitive things that we always believe to be true that aren't always true. Why is this little flag thing down here? I don't know. Please just ignore that. I don't know why that's there, but this has given me such a headache this morning that I don't want to play with it. Okay. Now, what about humidity? What does humidity actually represent? What does that mean? Right. The concentration of water vapor in the air, right? So let's look at a graph. There we go. The top graph. Just ignore the bottom here for a second. So the top graph shows us that what? How would you summarize this graph? The relationship between absolute humidity and temperature is what? Generally, I'm not looking for like a yeah. So they're generally positively correlated. The higher the temperature, the higher the absolute humidity. Meaning, and this meteorologists despise when you say it this way, but this is how we always say it. Hot air can hold more water. The word hold irritates the crap out of scientists because it's not really, it's not really holding on to the water. It just is able to allow more water vapor to exist. Before it reaches this point along this line, what's this line called? Or what is this, I should maybe restate this. What does this line represent? Saturation. What is that? What's a kind of more common term that we use for saturation? The dew point, right. So this line represents the dew point. So if we had water at 10 degrees C, and it had an absolute humidity of about, I don't know, 10-ish, it would be 100% saturated, right? That would be its dew point. That means if we take warm water, let's see, let's take our warm water here and cool it down, or let's go here, like warm water with, say, about 50% humidity, warm air, I'm sorry, I'm on my wrong fluid, about 50% humidity, and we cool that air, eventually what happens is that we condense it, right? That's basically all this graph is saying. This actually follows what our intuition knows, that hot air has the ability to contain more water vapor than cold air. And I put this in quotes just to remind us that scientifically that's not always the way we like to express it. We're going to just skip over this relative humidity stuff. I guess when we do follow-ups, I don't get to see all of you. All right. When we do follow-ups, I'll send some stuff along, some cool applications of absolute relative humidity to the professors that are working at your satellites so that we can kind of investigate this a little bit further. Anybody ever used a sling psychrometer?
Yes.
Yeah, that's kind of a fun, dramatic way to show cooling evaporative processes. So let's just move on. All right, let's talk about gradient. I promised we'd talk about density and gradient. Again, this is a topographic contour map. We have a steep slope over here, a gradual slope over here. Why? How do I know that?
The lines are closer together,
Yeah.
further apart.
Right. So we're basically looking at an elevation change of 280 to 200, right? These are increments of 20. So we've got an elevation change of 80 meters. So I want you to come over here and calculate what the slope is. Here and here. Can you calculate the slope for me? How do we calculate a slope? Rise over run, right? So you want to know your elevation change. Okay, I've never in my life used a chalkboard to teach before today, so this is kind of fun. Rise over, maybe in grad school, but that's probably the last time. So what's our rise? Oh, and this one, you're right, it's different than this one. It's a 100-meter rise over here. So we have a 100-meter rise. What is our run?
I don't know what you mean by run, it's 5 gradients.
Run is the change on the surface of the Earth, the horizontal change. So this is the rise. Can you figure out the gradient with the information I gave you? No, absolutely not. You need a scale. And one of the other things that drives me most crazy is that maps that are produced without scales are sort of pointless. So I put a scale on here. I made one up. This is about 1 kilometer here. I said this was, I think, 1.25 kilometers. So we end up getting a gradient for this side, which is less than the gradient on this side, which supports our original supposition that this is steeper and this is shallower. So we're talking about weather. Why am I showing you topographic contours? Because I think the concept of a hill is probably easier for people to visualize than the concept of pressure isobars. Okay, so when we're looking at all of these equal potential, equal pressure lines in our weather maps, they represent hills and valleys just like our topographic contours. All right, so let's talk a little bit now about what creates the weather. This is something you teach probably, what, 4th grade-ish? I don't know. Yeah, what creates the weather to a 4th grader?
Well, you go through the whole thing, so you start showing the different symbols
Okay.
of how the weather, the maps and everything, and then you don't really teach whole thing, you start talking about it
Okay.
in 4th grade.
Okay. So when do you teach them what actually drives weather? When does that come? Seventh? Okay. So what drives the weather? Clouds. Ultimately, let's go back to the very beginning. What drives the weather? Okay, well the pressure is different because of varying, right, unequal heating of the earth. We have this beautiful earth that tilts to the side, which makes it much more interesting. If it were sitting straight up and not tilted, studying weather would be really boring. And if we didn't have landforms and if we didn't have a lot of other things complicating the issue. But at the equator, we know the sun hits the earth. Oh, you know what? I need you guys to do something. I really don't need to capture this all on. I just needed to like blow up some earth for me. Like one every other person. We're going to work in teams for this. But while I'm working through this, we can use some hot air. So we've got right at the equator the most direct incoming solar radiation. As we go to the poles, that radiation comes in at a much weaker angle, and so we get changes. There you go. In the incoming solar radiation that ultimately determines our climate and our weather systems. All right, while you're blowing up those globes and you're happy, I'm going to show you a little bit of chemistry, or physics, I suppose. What is this? The ideal gas law, thank you. This is the ideal gas law. It states that pressure times volume equal a constant, the number of moles times a constant times the temperature. This is why I gave them to you. If I had to blow them all up, I'd be flat on the floor. Alrighty, so as we are blowing up our globes, give me an application of how you teach the ideal gas law, or how you demonstrate it. Anybody teach the ideal gas law? Not so much? No one? Well, I can guarantee you probably have demonstrated it, even if you don't realize it.
Individual laws opposed to the ideal.
Okay.
You know, Charles.
Yeah. Boils, right. Right, okay. So let's think of an example, a real-world example of how temperature, volume, and pressure in a gas are related to each other. I think this happens with my students a lot because I teach deep earth processes. We are so used to thinking about pressure as being 1 atmospheric pressure, maybe less than that if we go up into a mountain. But for the most part, our pressure here around the surface of the earth is fairly constant. And so we're not used to thinking of pressure as being able to change the phase from solid to liquid or gas, but in fact it can, right? So you have a compressed cylinder of liquid something. What's a compressed liquid gas? Oxygen. Is it liquid when those little tanks are liquid? Okay, so we compress the oxygen into a liquid form in our oxygen tank, and when we need to get that oxygen into a gas form, what do? We decrease or increase something. What do we do? Increase it or decrease it?
Pressure decrease.
Right. So in that tank, it's compressed. It's under very high pressure. When we bring that pressure down and we decrease it by opening that valve, what happens to that liquid? It actually is able to expand and become a gas. Let me see. You've probably done something maybe with, there's a really cool experiment with liquid nitrogen and balloons, but in your classrooms, maybe you've done just like the collapsing soda bottle in warm and cold air. So you can put, just a plastic 2-liter bottle and pour warm air in it, seal it. Pour
And
So-
ice water.
soda can. How do you do that one?
Well, you just take the lid off, take the little tap off, and just let it either heat it up in hot
Right.
water and then put it in the cold water.
Okay, right. And so the bottle will either expand, or more often than not, you're going to do it the opposite direction, put it into the cold. Because the temperature is decreasing, we have to see a corresponding decrease in the volume. That's what the ideal gas laws tell us. Anytime you change one of these things, something else has to readjust. Now, atmospheric scientists prefer to use a slightly different version of the ideal gas law because volume measurements in the atmosphere are a bit challenging. So they tend to prefer to think of things in terms of density, which again is something not that far from what we did with that paper bag on the pendulum. We basically increased the temperature of the air in the one bag on the one side, which decreased its density, right? So if all things stay equal and all we're doing is increasing temperature, density, if we're going to keep the pressure constant, this already is constant, the only thing that can change is density. So when we raise the temperature, we have to lower the density in order for this to stay balanced. It's as simple as that. This little guy is called rho, just in case you're not used to the Greek scientific notation. Yeah, and here's the example that I was just talking about. We can actually change the density of a gas by altering its pressure. That's all that these ideal gas laws tell us. Let's see. All right. So I'd like you to kind of we're going to kind of look at this, but I don't have time to dig into this a whole lot and get through the material we need to get through today, but you can kind of test yourself with this. The bottle example, the compressed gas example, the heating of air examples. You can kind of say, okay, if I alter this, just temperature, what's going to have to happen to my density? All right, this is actually a little animation that, where'd it go? I'm not going to actually pull this up, but there is, where is it? I don't know why this is being all weird. Oh, here's the applet. We'll see if it works. This may throw this computer over the edge. Yeah, I'm just not gonna. Okay, maybe it'll run. This is probably stretching it for, this is exactly what's been going on. I accept. We'll see if it works. Yeah, so you guys have probably seen this. So you can get in here and you can pump up the pressure. You've done this one. What's PHET exactly?
That's the
but
That's it.
what does
That's
it?
it, you got it.
No, but what does it stand for?
No.
Oh, okay. Because okay. So you guys have seen this and played with this, but you can change the heat, you can change the pressure, you can kind of quiz. Okay, so if I add some heat here, what's going to happen? Nothing else is changing. If I add heat, what's going to happen to the temperature? We know what's going to happen to the pressure.
It should go up.
What about if I hold? Oh yeah, it went up a little. Let's hold the pressure constant. Then what happens? Ah. Okay, this makes me a little crazy. You can only hold so many things constant, right? Let's turn the heat back off. Is he trying to push it back? All right. So you guys have probably, what the heck is going on? Now it won't let me get off of this page. All right. I had a feeling opening that was going to not be pretty. So again, like I said, we often think in such terms of what happens at our Earth's surface temperatures and pressures that we forget that up in the atmosphere, pressures change dramatically, and down deep in the Earth, pressures change dramatically. When you want to boil water, how do you do it? You add heat, okay? If you can't add heat, if you want to boil water, how do you do it? Well, I'm not sure, so let's write this up and find out. So, I can't change this. I've said that's a constant. These are constants, these are constants. I want to change, what did I say I wanted to do? I wanted to boil it. So what can I do?
Change the pressure.
Do I have to increase or decrease the pressure?
Increase.
All right, so let's go to the top of Mount Everest. All right, so if I were at the top of Mount Everest and I wanted to boil some water, at sea level, our water is going to boil at 100 degrees C, right? What temperature is it going to boil at a higher or a lower temperature when I go up in the atmosphere? At a lower pressure. Okay, the pressure up at Mount Everest is lower, right? So if this goes down, we're not constant anymore, the temperature is going to go down, right? So actually, if I boil water here in wherever we are, what is this, Exton? About 100 degrees C, I boil water. I go to the top of Mount Everest, it's about 77 degrees C that I boil water. You know a really practical application of this that maybe your grandparents or campers or people use? Anybody ever used a pressure cooker? Yeah. So a pressure cooker uses the same idea. If I increase the pressure inside of my cooking vessel, guess what happens? It cooks at a higher temperature, which means I cook it for a smaller time because ultimately it's the amount of heat you're putting on the food. So if I want to boil an egg here, what, 7 minutes? Maybe? If I want to boil an egg, if I wanted to carry an egg to the top of Mount Everest, would I have to boil it for more time or less time? This is just kind of a curiosity. You have to boil it for more time because you're applying less heat. You're only applying 77 degrees C, so you have to apply it for over a longer amount of time. And anybody that lives in Colorado will tell you baking is tough. It's really tough to adjust from baking here to baking there because of the differences in pressure. So we're gonna really stay focused on the lower atmosphere, the troposphere. If you were to draw a graph here, relationship between pressure and temperature, what's it gonna look like in the troposphere? So as we get, okay, so this is a lower pressure. This is a higher pressure. It's kind of upside down. But this is, they kind of orient you this way because, you know, here's kind of maybe where we're standing, and here's up in the atmosphere. So that's why the graph is oriented sort of reverse mathematically, but it makes sense intuitively. So as we get higher in the troposphere, what happens to the temperature? Oh, I'm sorry, this stupid banner is covering your numbers. Okay. So again, the temperature is getting higher in this direction, right? And so what we see is a relationship where as pressure decreases, temperature increases, which means we're standing here at the surface of the Earth. Our temperature, all things considered equal, is going to be more than the temperature in the other upper atmosphere, which is kind of intuitively what we already know. In the troposphere, what happens when we get to the stratosphere? Exact opposite, totally flip-flops. So let's look real quickly. Here's the troposphere. This is where our weather happens. This is what we're going to focus on. But just for completion's sake, these are the rest of the layers of the atmosphere. Here's a sort of combination of the temperature and the pressure on one graph. And something interesting happens in the stratosphere. Anybody know why this is warmer? Go ahead and tell us. What happens? Right. So when ozone is created, and the stratosphere is where our stratospheric ozone is created, we also have low-level ozone, but that's slightly different. So in the stratosphere, the process of making ozone is actually exothermic, and so we give off heat. And so it's kind of interesting, once you get to this tropopause, this relationship starts to reverse. And as we get higher in the atmosphere, it gets warmer, and then it flip-flops again, and it flip-flops again. We kind of have this zigzag relationship. So you really have to know which layer you're working with when you're talking about relationships between temperature and atmospheric pressures. And this is kind of just some notes going back to what she was explaining to us. Okay, this is really going to annoy me here. How do I don't know what I'm supposed to upgrade, but that footer is not going away for me. I guess we'll just deal with it. Okay, so a quick review of what atmospheric pressure actually is. It's basically the weight or the density of the atmosphere pushing down against you at any point on Earth's surface. That's why here, near sea level, we have a higher atmospheric pressure because we've got a greater amount of atmosphere pushing down on us than when we go to the top of Mount Everest. There's less atmosphere actually pushing down on us. These are some average sea level pressures. Most often in meteorology, they report them as millibars. Historically, we reported them as mercury, centimeters or inches of mercury. If you're into PSIs, it's also equivalent to about 14.5 PSI. Atmospheric pressure at sea level. Different types of barometers. This is kind of where we started with water and mercury barometers. This is where we are now. We have what we call an aneroid barometer, which is basically a chamber of air that will expand and contract as the pressure changes. All right, so I brought along this little device that I've had in my house in a box for years, and I never actually brought it out. And I was like, well, that'd be kind of cool to take. So I need somebody up here. We're going to record pressure throughout the week on this and compare it then to the actual pressures that are reported by NOAA, so we can see if our qualitative assessment is close to the quantitative assessment. So you want to come up and mark our pressure up here? Sure. You look like you could use a little stand up for a second here. So all I want you to do is take the pen, and literally what you're looking at is not this level, but this level here.
Oh my God.
So,
Can I turn it?
well, just kind of wing it.
Wing it?
Yeah, just maybe this line. About there. If I turn it too much, it's just
Like
going to...
here?
Here. Does that help?
Yeah, that's pretty good. So
Okay.
just put a line here?
Yep. And just
And
write...
today's date?
Just write Monday. What time is it? Monday noon. It's noon already? Oh. Okay. All right, so let's also put on there the pressure right here at the Philadelphia airport is 1018.3.
What do you call this apparatus?
It's called a storm glass or a pilgrim barometer. I've heard pilgrim glass, storm glass.
You can get it in a chemical supply company under weather glass.
Weather glass, thank you. Okay, weather glass.
Like that?
Perfect.
Okay.
That's good.
Probably should have written those
That's
so
fine.
close.
That's fine. That's
It'll
perfect.
change.
Yeah, so, you guys maybe remind me when we get back together. We'll see where that went this week. But the way it works is pretty slick. In fact, this level, when was this? Last week when we had this crazy weather system going through, this low weather system going through, this water was bubbling out the top. It was just spewing. Because what it's measuring is how much atmospheric, this is basically a sealed glass container, and this is an open hole right here. And so it's responding to changes in the atmospheric pressure. So when the atmospheric pressure is high, this water level will go down because it's pushing it down. And when the atmospheric pressure is lower, this will move upward. So it's a nice, very easy, and they're not really expensive, are they? I mean, they're pretty cheap, yeah. I bought this one years ago at like a home goods store that was going out of business and never hung it up, and now I think I might have to go home and hang it up. But. All right, so we can also look, this is actually a live Where's my thing? This is a, whoops, a live display, current pressure in the United States. Let's see if it agrees with what we just saw. This is about 1018. This line here is 1020. Now they go in increments of 4, right? No, this must be 2. Are these increments of 2? They're supposed to be 4, but that looks like 2 to me, right? Yeah. So this is saying it's 1018, which is right about what we found, right? Actually, it was 1018.3, which makes sense because this is 1020, so we'll go higher as we move in toward where we are off the coast. Alrighty. Everybody have their blown up globes. Good. All right, so out of curiosity, I kind of what's it doing? All right, so I was kind of curious. What are some of the lowest and the highest atmospheric pressures ever measured? About 1013, 1015 is considered average. Anybody know how low or how low or how high we can go? 960-ish? Okay. What else? Anybody know any of the highs? Out of curiosity, what kind of climates do you think we see the lows in? What kind of climates do you think we see the highs in? Ooh, good answers. You usually tend to associate these low pressure occurrences with warmer climates, and we'll get to that in a second. So this is about average right here. The lowest pressure ever measured was a typhoon tip in 1979. The pressure actually went down as low as 870. Yeah, I know, crazy, right? The highest ever recorded was in Siberia. Surprise, surprise. It's kind of what we associate with Siberia, crazy kind of climate. So basically, cold climate is what we associate our highest high pressures, and very warm climates, Hurricane Camille, Hurricane Hugo, Hurricane Andrew. All these tropical stirrings. You can't generalize it that easily. It's just the low, but you can say sometimes it's dangerous to make those generalizations, but you can say that the lowest recorded temperature ever was in a warm climate, and the highest recorded, pressure, not temperature, I'm going to do that all the time. Highest recorded pressure in a cooler climate.
What about tornadoes, like inside and outside the tornado?
Well, you're setting up an extreme system, so you're going to have very low lows as well inside that tornado. Okay, just like a hurricane. You know what? We're not going to go through this. Let's talk about this. Contour maps again. Just for those of you that are not used to working with these, what these isobars represent are equal pressure. They're equal pressure lines. So everywhere along this line is 1,000 millibars. Everywhere along this line are 996 millibars. So if you want to find where 998 millibars is, you probably, if it was a linear relationship, you could go right to the middle and say, boom, right there, right between the two. You can kind of interpolate that visually too. It's not dissimilar at all from what we do with contour maps on the ground. All right, so let's look at how we go about doing this. This is a pressure map I pulled off, I think, last week. So just visually, you guys may have a hard time seeing these numbers. Does anybody see like where a low pressure seems to be on this map? These are like the thousands. These are 900s. Anybody see a low pressure in here? 61 is low. What about 928 in northern PA?
931.
Why am I not seeing that up here? All right. So if if you were my students and we had more time, I would ask you to go through this process of contouring these, but because we have limited time together, I'm going to kind of pop up a map, and hopefully it will help you visualize how we take this data in sort of a grid format and make it into this type of map, all right? So in this map, you were right, we had a low pressure system forming right around that 920 something value. And we had, basically going out from this low pressure system, increasing pressures, but we also did, somebody noted there was this low pressure up in northern Pennsylvania. We also had that pop up on our map too. All right, so now we're going to get in the nitty-gritty details. Wind. How do we generate wind?
Change in pressure from low to high.
Which direction?
Toward low from high.
Right. You all know this. We always in nature go from a high potential to a low potential. We are going from a high pressure to a low pressure. Again, consider the fact that this wind is blowing over a friction surface, a surface that induces friction. So if we had an ideal planet where we didn't rotate and the sun, wasn't tilted and all this other stuff, actually that wouldn't even matter. If we had an ideal non-rotating planet, this would be so simple. Our conversation would be this. Pressure drives winds from high to low in a perpendicular fashion. When you're walking down a hill and it's really, really steep and you don't want to trip, you don't walk down perpendicular to the steepest gradient. You tend to go off to the side maybe, right? The steepest gradient is going to be perpendicular to those isobars. That's kind of important to remember. This is the steepest gradient right here. If I went off at an angle, that would be a less steep gradient because I'd be traveling over a longer distance for the same elevation change. However, we do have a rotating Earth, and so we have to account for it. We account for it with the Coriolis effect, which you all know deflects winds in what direction? In the northern hemisphere. Right or left? Okay, so your air parcel is moving in this direction and is deflected in what? As you're looking down. Okay? So as you're looking down, it's deflecting to the right. Right? Think of this as a flat circle. All right? So you got to look down at it from the top. I know. The way they drew this graph kind of, you have to flip it in your head, but it's deflecting down to the right. So anytime a wind parcel flows along the surface of the Earth that's not at the equator, it will be, in the northern hemisphere, deflected to the right because of the rotation of the Earth. So let me borrow one of your globes. You're going to prove this to yourselves in just a second. Why don't we go ahead and just hand out some of these dry erase markers. Guess we'll have to get theirs too because we only have 2 here. So we're going to work in teams of 2. But basically, if I'm an air parcel and I'm moving, which way is the globe turning? This way? This way. Right. So the globe is turning this way. So if I'm an air parcel and I'm going on a straight trajectory, I'm going to do my best to go straight. From my bird's eye view here, that wind parcel is being deflected to the right. Okay? So along the wind's path to the right. So you always have to kind of put yourself in the position of, I am the wind particle. I am the air parcel. Not the wind, the air parcel. All right, so what I want you guys to do is one of you be the rotating Earth. I guess we can. Okay, one of you be the rotating Earth. Do you guys, I have your Earth. That's why you don't have one. And make sure you're rotating the Earth in the right direction. The other of you do the best job you can to draw a straight line as they are rotating. And let's see what you've developed here. You didn't rotate it.
We did on
Oh, you're doing it better. Okay. I got it. How do we do? Woohoo! They got all kinds of waves. And
She erased part of it.
that's okay.
It was pretty much.
It's doing what you need to do, right? It's deflecting. Okay. So I love using these plastic globes. You can certainly do this demonstration without the globes, with a piece of paper. All right, so maybe I'll just do this with one of you. Here, do me a favor. We're going to rotate that paper in the direction that the Earth rotates. Is that right? Okay, so you do that while I'm drawing the line. So go ahead. No, that's the wrong direction. Hold on. The Earth goes,
I'm looking at Earth. Or am I looking down?
go like this, right?
That's what I was doing.
Is that what you were doing?
Do you mean,
Yes.
is this the
Yes, if
north?
this is the North Pole.
Okay, so yeah, it needs to spin that way.
Okay, so let's go ahead.
Because it goes,
There we go, that's better. All right, so you can also do this with a piece of paper and a ruler. And you just basically, have one person hold their pen against the ruler while the other person makes sure they're spinning the Earth in the right direction, which we were having difficulty with. So, obviously you need to give your students a bit more direction there. But they're both really nice examples of how the Coriolis effect works.
So whether you're going from north or
It's only, okay, it only deflects to the right in the northern hemisphere. Let's flip the globe. Flip the globe and let's see what happens in the southern hemisphere, just to make things confusing. So do the same thing, turn the globe in the right direction, pretend you're a parcel of, sorry, not a parcel, yeah, a parcel of air coming from Antarctica. And what happened? Which way did it deflect? Yeah. It's a mirror image, right? So you basically deflected your Coriolis effect to the left. So I could show you a high pressure system with winds going around it, and you could tell me if it was a northern system, a north hemisphere system, or a southern hemisphere system, right? So if we've got a low pressure system here, well, we're going to work up to this. I don't think we're quite there yet. Alrighty, so that's what we were doing with the globes. This is what it looks like in a more, if you want to think about what all the different vectors are actually doing, this is kind of crazy. When we look at winds, we sort of have to look at winds aloft, high-level winds, and we have to look at surface winds slightly differently. Aloft, the winds are affected by the pressure gradient and Coriolis effect. When we look at winds along the ground, they have one more force acting on them, and that's friction. So aloft, something kind of crazy happens. We are crossing these pressure gradients in a perpendicular direction, right? That's what going from high pressure to low pressure does. The Coriolis force deflects us to the right. So here's our main trajectory. The Coriolis force pulls us off to the right, which makes our wind be this purple arrow here. If we keep going, we actually can set up a condition in the upper aloft winds that aren't affected by friction, where the pressure gradient force, that force that's driving us across the isobars, is exactly balanced by the Coriolis force. And we don't cross the isobars, we actually run parallel to them with our wind. This is what's happening in our upper atmosphere. We're going to more concentrate on our lower atmosphere winds, so we're going to add in that friction component. What's going to happen when we add in the friction component? Any guesses? It's going to slow down for sure. What's going to happen to the direction of this wind? You can kind of guess already it's not going to be parallel to the isobars, right? And we know it can't go this direction, right? Because that goes against nature. We can't go from low to high. So we know most likely it's probably going to be deflected in this direction. So we're still going from high pressure to low pressure, but at a different angle than our surface level winds. Okay, we're going to skip through this. Just for those of you that are interested in the physics and the math of this, We do get a strong Coriolis effect at the North Pole and a zero Coriolis effect at the equator because it's a sine relationship anyway. These are our geostrophic winds. This is just another kind of cleaner image of the vectors. All right, so let's throw in friction. Let's see what happens. All right, so we kind of had this sense that we knew that this this air parcel had to go in this direction from high to low. We've got the pressure gradient force always driving us perpendicular along these lines. We've got friction kind of pulling us back this way. It's working against the direction of the wind moving. And we've always got this Coriolis vector spinning off to the right, pulling the whole movement off to the right. So we now, with our surface winds, are crossing these isobars. Our upper level winds, we were not crossing these isobars. I know, guys, I'm sorry. This is a tough time of the morning. Just get into this stuff. All right. All right, so what this sets up for us, these are upper level winds. We know that because the winds are running parallel to the isobars. These are surface winds. We know that because our wind vectors are crossing the isobars. In a low pressure system, we want to go this way, right? We want to go directly there, but we're always deflected to the right. So what happens is we start setting up, I want to go this way, but I'm deflected to the right. So what we're setting up is what kind of directional flow? Counterclockwise. I'm like, did I hear that right? We're setting up counterclockwise. What's another word for this in meteorology? No, we also call this a cyclone. All right, so they mean the same thing. And of course, I'm going to go through this. There's a nice animation that shows this much more clearly than my drawing over there. I think that's what's coming up next. But basically what happens then is at a low pressure system, you have typically associated with bad weather, I said L for lousy, so you can kind of keep that straight. And at a high pressure system, you have H for happy weather, to keep that straight. Love mnemonics. We use mnemonics all the time. Where was I going with this? Oh, okay, I know where we were headed. So a high pressure system. Think of a high pressure system as the air column above this center putting a lot of pressure onto the Earth. So we think of high pressure systems as having air that's sinking. As it's sinking, it's putting pressure, it's adding to the atmospheric pressure. The opposite is true of a low pressure system. Where we have a low pressure system, we think of the air as lifting into the upper atmosphere, releasing some of that pressure from the atmosphere and making it a lower pressure system. We're going to talk about this. We'll probably run out of time today, so we'll talk about this a bit next time I see you guys. But traditionally, we had these barometers that often had indications of what kind of weather to expect, right? This is a perfect example. When the pressure was falling, our barometer tells us that the conditions outside are deteriorating. When our pressure is rising, tells us that our conditions outside are improving. So what do you think happened to the barometer between yesterday and today, if you had to make a guess? Yeah, it went beautifully over into this direction. It went into the high pressure, happy end of the spectrum. Typically, this is like a postcard picture of what a high pressure system can do. It doesn't, in our humid Pennsylvania climate, always bring quite this lovely weather, but it tends to improve the weather, even if it's only for a short duration before the next crazy front comes through. Okay, so this is really, I think this animation is great because it takes you from the perspective of the air parcel. You want to go perpendicular, but you're going to twist off to the right because of Coriolis. So again, from here, you want to go perpendicular. Imagine the circles around here. but you're going to get deflected again off to the right. And what we're doing, you can see this is setting up a clockwise or an anticyclonic flow. You see how that works? It's pretty slick. You have to think of yourself, be the vector, okay? Be the vector and think of yourself going across those pressure gradients. And as you are the vector, you're always going to deflect yourself to the right. That way you don't ever have to memorize anything. You just have to remember those simple facts. You don't have to memorize what is an anticyclone and what is a cyclone. So yeah, this is like one of the best animations of this I've seen. We can do the same with a low pressure system. No, we can't. What do I do? Click here to... That's going to close it. I guess I can't get there. Yeah, you know. Technology is great. Okay, I hate Windows 8. I don't even know how to get back to my original. Anybody, I mean, Windows, whatever this is. Does anybody even know?
Get more information.
Yeah, we're just going to skip, hopefully, on to our next thing here. No, I got to get off there. All right, well, if that little applet had worked, we would have seen the exact opposite thing happening around our low pressure system. The low is going counterclockwise, right? So as you're crossing the parallel isobar, you're going to deflect to the right. This sets up counterclockwise flow. It's what? This is a cyclone. An anticyclone is formed around a high pressure system. Remember, when I'm telling you these things, this is only for the northern hemisphere because you guys kind of showed yourselves, right, that it works quite differently if we are leaving Australia and heading towards the equator. All right, let me think. I need to make a note of where we're stopping with you guys. Yeah. All right, so let's do a quick review here. Around a high pressure center, the winds move what direction? Okay. Around a low pressure center, winds move? Excellent. Again, there's no need to memorize this. Grab a piece of paper. Let's prove it to ourselves. Set up something that looks like this. There we go. Give yourself a high pressure system and a low pressure system. And before you can leave for lunch, prove to me that you know which way the winds are going to go. Do a dashed line for the pressure gradient force. Do a deflection to the right for Coriolis. And I want to see for sure that we have this down before you can have lunch. So remember, be the vector. Be the vector. The vector wants to go this direction. And in our high pressure system, you're done? You can go to lunch now? So in our high pressure system, remember our pressure gradient force is taking us from high to low, so we're going this way. But then we have to veer to the right off that path. So let's see.
Oh, we didn't draw dotted lines.
That's fine. All right, you're good. You can go to lunch. I'll see you guys in a few days. I don't know when again, but how are we doing? Where's our high pressure and low pressure system? Come on, this is not a group effort.